Good afternoon, gentle readers. It's March 10th, 2025. And today in Logos 2000, continuing in the consideration of the history of foundations of philosophy and science and mathematics and logic and physics. Foundations. Here from the state of Idaho in the United States of America. From a study of Ross Finlayson. Here is today's Logos 2000. What we'll be doing today is looking at some of the stacks of books and differential equations. Because I was trying to figure out a little bit more about it, since these studies, and for example, in the descriptive differential dynamics in this bit, and the that particularly, and then also in the moment in motion with regards to the higher orders of acceleration. And with regards to the integral and the differential, and the idea that the differential is results of value, and the integral results in indefinite value in terms of the functions and their usual treatment, as with regards to the fundamental theorems of the calculus, the fundamental theorem of the differential, and the fundamental theorem of the integral, or the derivative in an integral. That I thought to kind of take a quick survey of some of these books in mostly the differential analysis, but some in the integral analysis, and just to try to get an idea of where that would stand today, later in this discussion, later in this course, insofar as what's gone on over the past couple years or so on these podcasts has seen not only like recapitulation of existing and the linear curriculum and this kind of thing, but some kind of novel developments, this original analysis, and the idea of the identity dimension and these kinds of things, and the stop derivative, and the walk integral, and the differintegro systems that work to evaluate for the infinitely many higher orders of acceleration and the immovable object and the unstoppable force, how it works out that any smallest change has infinitely many nominally non-zero higher orders of change anytime. The L at one time, that it works out in this way, that those being the discussions here, that they also include the discussions about continuity and infinity, that there's at least three models of continuous domains in mathematics, in the domain of discourse, the universe of objects that are mathematics' objects. There's at least three kinds of laws of large numbers to reflect upon these, three kinds of Cantor space, all the zeros and ones in a space, and that those are also not usually part of the standard linear curriculum, but they are part of mathematics. And then insofar as then they can be solved together, because otherwise they would be contradictory in terms of some of the inductive accounts that can only merely be partial and half inductive accounts, that without this fuller, wider dialectic of the deductive analysis to arrive so at these constructive accounts together of these objects of mathematics in function theory and topology, as it's so described in these hundreds of hours of lectures, that it would be a great onus, a burden upon the conscientious mathematician to make this so. Because if it's not otherwise made so, then it's essentially hypocritical or in a sense criminal to the conscientious mathematician and conscientious logician to aver that these things are not so together. So that just kind of sets up that in this manner, I would point to others, and I generally do, is with regards to what other matters of truth has been collected, like Greek idealism, German idealism, the analytical tradition, and these things which result today the best and premier theories we have, tempered with the wisdom that that some things were left behind and they cannot be done without. So that combines this ontology and this idealism to make for a merest, briefest teleology, the silver thread, the Shastra connecting us to continuity and time. And that then there's also that, for that being the temporality and the modality of what can only be the sort of a one true logic, the logic, not magic, logic. That thusly an ontology can be so equipped with as Derrida and Husserl put it early in the 20th century, something along the lines of the what arises from the pre-geometric, pre-scientific world to our living world, and that then that's just the realm of our intersubjective and empirical, insofar as that in the maturation of the philosophy, in the study of it, that this is how it so kind of arrives at what results as a thorough, kind of culminating, fulfilling account of why otherwise what would be deemed lacking would eventually not fulfill the goal of foundations, which is a theory. A theory. Here, a theory, A for the letter A, and also just for the particular indefinite article, the theory. So let's see what these books have to provide today as we might arrive from the stacks. Let's see here. What we got is some books in differential analysis. So this is Partial Differential Equations for Scientists and Engineers. Stanley Farlow's Dover reprint, who's a professor of mathematics at the University of Maine, has published this work in 1982 and 1993. Then it's also copyrighted, as published by John Wiley, Partial Differential Equations for Scientists and Engineers. And it describes that this is for to stimulate intuitive thinking while not losing too much mathematical accuracy. It is possible to wave away all the subtleties which here are not allowed to be dispatched without being kept in as to how they're dispatched and why they're dispatched and so on. As with regards to a comment from Quine the other day in Word and Object, he said, it is one of the great things about philosophy compared to logic, where kind of in logicist positivism, when you've dispatched from something to find it away, that it's gone, that instead there is no such thing in this truer thing, which can also be a logic, which can also be a scientific logicist positivism, altogether a great logicist positivism. So when the author here describes smoothing over some of the subtleties of differential analysis, it goes without saying that approximations always have non-zero nominal error terms, and partial differentiation is partial. And there are cases, according to basically saddle points, where they are not merely possibly intractable as incomplete and inconsistent to be declared complete. So it talks about separation of variables and integral transforms are the two most important analytical tools discussed, or analytic tools as he puts it. Several non-standard topics such as Monte Carlo methods, calculus of variations, control theory, potential theory, and integral equations are also discussed. These are not non-standard in the sense that we'd usually say that standard means classical and not infinitary. So here non-standard means infinitary reasoning. And so these we would just say enrichments or particular subfields or fields of application. Monte Carlo methods involve the stochastic, and basically that involves the hypotheses of small perturbations, the variational principle, and the Virier principle. Those kind of being the same thing about the idea is that when we reach a local minimum or maximum that isn't a global minimum or maximum, you have to have some way to kind of like stimulate it to get out of that rut that it's in terms of falling or rising to a greater global minimum or maximum. The idea is that that's where it should go, these kinds of solutions. So Monte Carlo is an approach to that, and then also this variational principle is an approach to that. And then control theory and potential theory. Control theory is often about the idea of given inputs, how can we arrive at output? And then potential theory is like usually the concerns of the space, the wider space. It's kind of the opposite of the classical theory. Let's do vector addition, to how potential theory is that these things all fall together in all of them. And integral equations, the complement of differential equations. Usually there'll be a differential equation, and one of its solutions results basically an integral equation, and one of its plane curves or solutions results that same differential equation, but there are others. And so the insides and outsides of differential and integral equations is that here, after descriptive differential dynamics, it was read up that there's to be a much more even-keeled treatment of the differential and the integral equations for the mensuration and the tangent. The idea being that these come together in particular ways then as with regards to the plane curves of integral equations and the solutions of differential equations. So the differintegro and the integro differ are where equations always have both integral and differential components that define them. And so there's just a general idea that all integral equations and all differential equations are also both of differintegro and integro different equations. In terms of any kind of real system that affects to reflect that the tendencies and propensities, and as with regards to the restitution and oscillation of the dissipation and attenuation, and that basically is setting up everything that goes into least action and least gradient for the sum of history, sum of potentials theory called physics and the foundations thereof. That having that each of the integral and differential systems really is a differintegro and an integro differ system, then gets into a lot of the other accounts of the treatments of things that it would avert to solve, to provide solutions for these things. So that here is kind of being established, is that it's so that when we talk about it would kind of be subsumed then under the integral analysis, because the differential analysis and then the partial differential analysis kind of has crumbled down to nothing left, which is its strength, that it's closed in that sense. But the completeness would be on the other side of that then. This book can be used for a course of 1 or 2 semesters. It assumes only knowledge of differential and integral calculus and ordinary differential equations. Those with kind of elementary or ordinary solutions. Diffusion type problems, boundary conditions for diffusion type problems, derivation of the heat equation. So here we got our great derivation of the heat equation from Gonzalez Velasco's book on Fourier and the heat equation and boundary value problems. Transforming non-homogeneous boundary conditions into homogeneous boundary conditions, solving more complicated problems by separation of variables, transforming hard equations into easier ones. PDEs, eigenfunction expansions, sine and cosine transforms, the Fourier series and transform, the Laplace transform, Duhamel's principle. Now, I'm quite interested in Duhamel's principle because the way it is that in the Lorentzian, and as for the Laplacian, that the Duhamel principle kind of is like that missing nominally non-zero term that should go in there. So I'll probably look here to the Duhamel principle. And then we get up into the D'Alembert solution, and so we got D'Alembert in the wave equation, and then we have things to do with regards to Clairaut and D'Alembert and the linear fractional equation, which have that the identity dimension is the envelope of their solutions of those being integral equations. And so so it's kind of like at the edge of that, kind of like dividing by 0, which is nominally non-defined, but it has the idea that the regular singular points of the hypergeometric are 0, 1, and infinity. So there really is a place in a way that it is the surrounds of that. It is the box that it is in. The string, the vibrating string, the vibrating beam, 4th order PDE, dimensionless problems, waves in 2 and 3 dimensions, superposition, the backbone of linear systems, systems of PDEs, the vibrating drumhead. Here, this was the Chladni functions, and it's described here as a wave equation in polar coordinates, but it says well with these other, with resonance theory, that up above wave theory is resonance theory. So we'll be taking a look at that a little bit. Laplace's equation, Dirichlet problem. And then he gets into numerical and approximate methods, and so then that gets into these means of getting into solving things, up to calculus of variations, variational principles, perturbation methods, as from reading from Gauguin, the hypotheses of small perturbations, or HSP, that those are employed in setting up particularly the non-linear accounts that otherwise the linear accounts would fail to provide. So taking a look here at Duhamel's principle on page 106, just kind of get an idea of the flavor of this author's work, has that Duhamel's principle has that the Laplace transform can bring out an interesting underlying phenomena concerning solutions of differential equations, in particular by algebraically manipulating the Laplace transform of the solution of P to E. We're discovering an interesting idea known as Duhamel's principle. So I'm going to relate this later to Duhamel's principle as introduced in Gonzalez Velasco, and then get into this. So it's talking about heat flow or the heat equation, and setting up the same kind of ideas with regards to the constant boundary conditions and time-varying boundary conditions, setting up out of this grab bag toolkit of differential analysis, and then setting up some substitution of parameters out of an ordinary differential equation, and then setting it for Laplace transform, and that it has a term, and then that and a difference of terms, and so that there's an equation between this transform and this in this matrix elements and some given surrounds and the difference of it, and then it's solved backwards is kind of like is via the dot product and taking the integral, or as the author puts it, by integration by parts, equals this integral, and then a product in terms of the function and this this difference term. And then he says, in other words, we have found the solution u of xt to the time-varying problem in terms of the solution to the easy problem. And as with regards to that, we have here that this sets up what's called Duhamel's principle. And so it's set up in a little bit different form, which is there's just like a middle term that's non-zero, as with regards to that, then compared to the wxt and the uxt, and then setting up that, and then resubstituting that back into the solution for the non-varying boundary conditions, which is as with regards to a linear term, and then an infinitary expression after the inverse solution of the transform, as with regards to a de Moivre Euler-Gauss sort of setup in terms of sine n pi x times e to the negative n pi squared t, the summation of all those for all the negative 1 to the n over n times 2 over pi, as with regards to 1 over 4 pi and these kinds of ideas. But then we have what arrives as this is the next equation. Since if we differentiate the infinite series representation for wxt term by term, it results in a divergent series, see? And then we get into the Duhamel's principle a little bit. So it's a little bit different setup, and it's really just saying that these this expression of the substitution comes back, calling that Duhamel's principle. But here Duhamel's principle is more of like that there's this non-zero inner product which would otherwise be to zero. And then here that it falls out that in the forward and backwards of these manipulation of these terms algebraically, what's left to arrive at here is pretty much only this thing that has the a solution to this heat equation with varying and non-varying boundary conditions in time. And so then the author goes on to read into the importance of Duhamel's principle. The problem just discussed, we were able to solve the easy problem with constant BCs, so we used Duhamel's formulas to obtain the solution to the time-varying BCs. Quite often, however, even the easy problem, constant BCs, cannot be solved analytically. What we can do, however, is observe the solution experimentally. In other words, we can rig a device that has constant BCs and experimentally measure the response. We can then use Duhamel's principle to find the solution for any time-varying BC boundary conditions. In fact, we have only to observe the response wxt to get the constant BC problem once. When we have the data, we can then solve the problem with arbitrary BCFT by substituting into Duhamel's formulas. And he says that there's another interesting version of Duhamel's principle that gives solutions in terms of the solution wxt of the alternative simple problem. knowing this formula, which is dot dot dot, allows us to find the response and this and that. So for more about the Duhamel principle later, is Duhamel principle has a great place in the solution to Laplacian, which is involved everywhere in terms of relativity theory and harmonic functions and the theory of potentials, that it attains to like a theory of all the potentials, which it can't quite be. And so it's another one of these things that has that, because there's multiple laws of large numbers, there are cases where it has different solutions in the infinitary reasoning. So that's something else to come up later. Tullio Levi-Civita's The Absolute Differential Calculus, the calculus of tensors. So tensors and the tensorial products make up for preserving metric and norm and as with regards to otherwise the transforms of the space. And so it suggests that there is a manifold and that the analysis is over the manifold as is if it were, that kind of like the measuring the line is an ant marching in a line and counting its steps, however so far it goes, assuming that its turn radius is 0. And otherwise that is the length of it. And so in a space then that's orthogonal and Euclidean, that's pretty simplified because it's just an area and then a volume. And then the tensors get into as with regards to like, well, given that the space is arbitrarily complex, this manifold, and when I say I meant originally say convoluted, but then we have to talk about convolution. And then saying complex also brings its baggage because it's a sector or a namespace of mathematical objects. But in the continuity of this manifold, it's not necessarily so a linear, so the unlinear, say, then the tensors make to provide to the notation that makes for the usual formalisms and forms of the vector addition, and so what results all such manners of the integral and the differential and having analytical character, say, over those. So let's take a look at what this says. And so Levi-Civita is very famous for this book and also as with regards to this whole idea. And then the umbral calculus. And so we have, if I'm not mistaken, about the umbral calculus as well. That gets more into recurrence relations and stuff like this. So this is by Tullio Levi-Civita, who is a professor of rational mechanics in Rome, in the University of Rome, and a fellow of the Roman Academy of the National Academy. Edited by Enrico Persico. Translated by Marjorie Long. 1926. Blackie and Son Limited, London and Glasgow, 1926. The present volume contains a complete translation made in consequence of a suggestion by my eminent friend, Professor E.T. Whitaker, FRS, of the Italian text of my Lezioni di Calcolo Differenziale Assoluto. 2 new chapters have been added, which are intended to exhibit the fundamental principles of Einstein's general theory of relativity, including, of course, as a limited case, the so-called special or restricted theory, as an application of the absolute calculus. So this makes me happy because general relativity is first, and special relativity is derivative of it, not the other way around. And so it's much simpler to kind of start with special relativity and then say there's a general relativity, but it's not full. It's not complete. So it's got to be the other way around. I've already had occasion to remark in the preface to the Italian edition that we possess very systematic and well-written expositions of relativity by celebrated authors. Here we point out Einstein, and it was read here out of my later years. The short treatment which is offered in the 2 new chapters of the present work presents some distinctive features which it may be well to point out explicitly. In the first place, in order not to increase the size of the book, he thought expedient to confine himself to tracing the relativistic evolution of mechanics and then of geometrical optics and to developing its most important consequences. So here, there's the reading of mechanics and moment and motion, and then that includes ideas about light. And then there's discussions here also in Logos 2000 about light, and the optical light is special. and in the realm of the bands of electromagnetic radiation, which also include that the electromagnetic radiation has kind of the long and the short waves, but light in the middle has no electromagnetic character at all. And then as with regards to nuclear radiation in the long and thermal radiation in the short wavelengths, then the geometrical optics says that geometric rays are not optical light. They're like about the opposite thing. The geometric means perfect angle incident reflections, and the optical means going around and the focus goes over and these kinds of things. So in our study here in mechanics, and we arrived at the world's turn, and for an inertial system, and as with regards to the fall of gravity and all that kind of stuff. And then with regards to the geometric optics, it's more like the optical geometry as with regards to how light sees it, as it were. In this treatment, the whole of electromagnetism is sacrificed, just left out. The sacrifice is certainly regrettable, since electromagnetism was historically related in the most intimate way to Einstein's conception, having served indeed as a support and model for restricted relativity. Furthermore, so he helps establish that special relativity was called restricted relativity. Furthermore, electromagnetism, in common with every other physical phenomenon, now comes within the ambit of general relativity. Much as the omission of electromagnetism is to be regretted, it has the advantage of reducing the program of subjects belonging to the pure Newtonian tradition or to its developments, and allows us to take a clearer, more exact view of the transition from the classical scheme of mechanics to the relativistic one. And he says, Einstein's discovery of the gravitational equations was announced by him in the famous note zur allgemeinen Relativitätstheory in the following words: Sie bedeuten einen wahren Triumph durch Gauss, Riemann, Christoph Ricci begründeten Methoden des allgemeinen differential calculus. And so the differential calculus, Einstein's relativity is an inertial system and is a differential system. But it's not necessarily a system of PDEs because they might not suffice. But it can be said to be an integral differential system. Here it says kind of related. It's also an integral system. So that just helps to reflect that these are what the tools they had, and they were the newest tools they had, and they were what were working for them. In an earlier memoir, Einstein had given a new exposition of these elements and formulae of the absolute calculus, which more specifically served his purposes. A similar standpoint was subsequently adopted by the most distinguished workers in the field of general relativity, in particular by Weil, Lau, Eddington, and Birkhoff. So I think Lau and needs a lot more standing, usually in the accounts, because like Weil is like a pretty big guy just because of real analysis and the Weil tensor and this kind of thing. And Eddington is a great proponent of relativity, as with regards to taking some plates and setting up the first kind of establishment. As kind of figured out here, it's like, well, that's not really like the reason why it's so. And the precession of Mercury, that's still like only half good, and these kinds of things with regards to what's observed and what's real. As with regards to measuring the speed of light, and the earlier experiment, or like Romer's experiments of the speed of light, helping establish that this 186,000 miles per second is not necessarily related to the 186 million miles. It's not just because it's not just some numerical coincidence that it's 186 million miles diameter of the Earth's orbit on average, and that light speed appears to be 186,000 miles per second. In terms of the solar year of the Earth and light's perceived speed in what is in the sky survey, what makes for these things. So Weil is already pretty big, but Lau, L-A-U-E, he deserves some more investigation and prominence in this kind of account because he was involved in some of the important developments in relativity theory. And then Birkhoff has got, in the Lacaniary, has some of the most important ideas that come up for the non-standard and the infinitary reasoning itself. So getting back then to like Ramsey theory and arithmetic progressions and are a variety of number theoretic conjectures, independent standard number theory, yes and no, multiple laws of large numbers, and these kinds of things that Birkhoff is known for these things. All of whom are reading as Levi-Civita, all of whom made conspicuous original contributions, both of idea and of method, to the physical theories, in addition to useful and elegant developments of the tensor calculus. Similar statements can be made for Carmichael, Marcolongo, Kopf, Becquerel, to mention from the vast literature on the subject only the books I have myself had occasion to consult, while de Donder has avoided the notation of the absolute calculus and used instead the theory of integral invariance. So that'd be interesting to look to see that then, because all this tensor calculus comes up as of about this. And so then this theory of integral invariance is kind of like about the regular singular points of the hypergeometric 0, 1, and infinity. And the singular integrals is read from Neri and is after, the school of Zariski and stuff like that. But then also for the great school of the integral analysis in the United States, later in terms of that being so relevant as a necessary perceived sort of complement in this. Just kind of like this, the earlier comment in this discussion has it so that there's always this nominally non-zero integro differ and differ integro. Here it's helped that Levi-Civita affects to reflect there's an entirely different school that's completely, or rather almost completely ignored, yet it has just perhaps as perfectly as well expressed the power, and it really needs both for them to attain to each other. Let's read on. In recent years, there have been some general treatises devoted to the absolute calculus, for example, those of Jouvet, Marais, and Galbrun. If I mispronounce his name, I would apologize. Lastly, there is another calculus in a new order of ideas, not less comprehensive, perhaps even more general, invented by Schouten, who's famous for tensors, and developed with the collaboration of Struik, who's a famous historian of mathematics, if it's not the different guy. Struik's name, or Struik or Struick, you'll see spelled variously if they're the same person. In face of this plentiful and valuable literature, a new discussion of Ricci's methods might seem to be superfluous, and conceptually this is perhaps true. So the Ricci tensor, though, with the Regi map and the Ricci tensor, is one of these important connectors in the middle of this tensor analysis that keeps these things from breaking apart, or is not meeting, say. So it might be that there are other ways to go look about that with regards to the convolutive setting and these other things that enable to make it so that what would otherwise be just a one-sided partial or half account has these both sides, but they kind of keep it in a box, in the windowing and boxing, which makes the NLS analysis. In fact, of the improvements and additions to the scheme of 1901, the memoir in mathematical and Annals of Mathematics, derived mainly from the notion of parallelism, and on this basis introduced by me into 2 courses of lectures given at the University of Rome during the sessions in the 1920 to 23. All or almost all will be found as independent discoveries of the authors already incited in one or other of their books. For instance, the definition of a tensor and some algebraic anticipations of the results intended to simplify the proofs are to be found in Weil, Lau, and Marais, all of whom, like Eddington, established a more or less intimate connexion between covariant differentiation and parallelism. Thorough discussion of the latter is also given by Jouvet and Galbrun. But the association with the algebraico-tensorial notation and with the elements of differential geometry is always less detailed and systematic than what I tried to establish in my lectures. The line of argument followed in them has a particular unity, which may perhaps justify their appearance in print at this juncture. The manuscript was edited with great care and intelligence by Dr. Enrico Persco from notes of the lectures. I wish to express my thanks to him, to his publisher, 1923. And then the references include Raumzeit and Materi, the Relativitat theory, mathematical theory of relativity, relativity in modern physics, theory of relativity, relatività, I fondamenti della relatività instantanea, the principe de relativity, la théorie de la gravitation, graphique einsteinique. Now this la graphique einsteinienne, see the gravific is different than the gravitic. The gravitic is like the Newtonian idea, and the gravific is the Faraday Lesage or the pull or the fall gravity. So when I see la gravifique einsteinienne from Paris, Gauthier Villars, 1921, I'd be looking to see what that's about. And that's said Donder again, and his theory of integral invariance. So D-O-N-D-E-R, Donder, with La Gravifique Einsteinienne from Paris, Gauthier Villars, 1921. That would be an interesting thing to look up. And then related to things like how the Duhamel principle helps to get from that one side of the usual absolute differential calculus into that integral invariant setting. An introduction au calcul tensoriel et au calcul differential absolu. And that's kind of like this work. It's also a coverage of sorts. Introduction géométrique à l'étude de la relativité. Introduction à la théorie de la relativité. Calcul differential absolu et géométrie. And see also in particular DJ Struik. Grundzüge der mehrdimensionalen differential geometry. So the ground rules or the way of the multidimensional differential geometry, which also contains a full and accurate bibliography, and also Schouten, that's Schouten, de Ricci calcul, also from Springer, Verlag. Alongside the extension of methods, there's a further point which I was unable to deal with in the lectures, but should refer to here, namely the extension of geometry beyond the already very wide boundaries laid down by Riemann. I alluded to the physical speculations of Weil and Eddington, which have recently culminated in a further generalization of the work of Einstein of the relativistic scheme. The spatial structure in relation to Weil's new concept of fine geometry has been the subject of study by Weil himself, whose results have been published in the volume Mathematische Analyse des Raumproblems. Of further important systematic research by Cartan and of numerous notes on special problems by Biewald, Bleschke, Dienis, Eisenhart, Kastner, Veblen, and others. So you might point to Veblen as kind of, he sets up after tensor notation and tensor indices and this kind of things. There's like Veblen notation, Veblen indices, and these kinds of things. Then the chapters in this book are functional determinants and matrices, systems of total differential equations, linear partial differential equations, complete systems, algebraic foundations of absolute differential calculus, which kind of it sets into invariance, covariance, and contravariance of a simple system with respect to linear transformations, dual variables. So take a look at dual variables for a second. Then he gets into ds squared and the line element on a surface. Here, of course, that's got its own formalism called the line reals. And then the Gauss-Bonnet theorem, which is a way to set up analytical character on a manifold. Parallelism with respect to a surface, and that's establishing right angles and straight lines, and also metrics and norms, because two parallel lines are also the same distance apart everywhere. So it's really about keeping a metric and a norm, like a distance here and the same distance there, and the metric and the norm, as with regards to things that are parallel, but they can be expressed in the same way, and teleparallelism and these kinds of things. With regards to mathematical notions, which make it so that the tensorial products are the same and preserve the affine relations, because that's all it really does, is it preserves the metrics and the norms, and thus the form and proportion and angles in geometry and the affine. That's what it does. They mentioned Christoffel and those having like all the different kinds of symmetries that begin to arise from the multiplication of symmetries, in a sense, the production of symmetries. Extension of the notion of parallelism, Bianchi's derived vectors. So Bianchi-Beckland, of course, is that's what they use today, as with regards to stuff like Ricci and Reggi, Bianchi and Beckland, these kinds of things. And finally, remarks on the case of an indefinite ds squared. So that's the infinitesimal, and affects things like from Richardson's, like two fields and whether they're meeting and their boundaries together, or they're already incident and they're falling apart. For something like Pauli principle, Wolfgang Pauli is like two particles do not superimpose. But the idea is, well, they either, as they're coming and going from that, then it's like not Wolfgang Pauli's way when these things are like so. And so for some people, that's like anathema to mathematics. And for other people, that's exactly what it is. So this is what it is here. So I was going to take a look at dual variables on page 67, and then remarks on an indefinite ds squared on page 141. Briefly. Coefficients of a linear form takes the coefficients of the new form as it transforms u bar of the u's. We shall then say that the u's form a covariant system. The new coefficients are there. Therefore, the u bars, okay, are the sum from I equals 1 to the n of the Cik ui. Interchanging I and k so as to get the formula in the same shape, it's the C the ki's, which gives the law of covariance. Usual formula, Kramer's rule, or Kramer's, it's spelled Cramer. You usually would think would be pronounced Kramer, but sometimes it's Kramer. So that's with regards to like Kramer-Rao, and then there's another Kramer though, and then there's also the Kramer in statistics is rules. And here's it's related to the convolutional setting, which sets up stuff from both sides. So it makes the same idea. You could also implement covariance in a convolutional setting. We shall frequently consider, together with the variables alpha, which are also called point variables, a system of covariant variables u called dual variables. The behavior of both sets of variables when a linear change of variables is made is shown by formulas 5 and 6, which is that they're respectively inverses of each other. Define a geometrical interpretation of dual variables. And so this gets into the covariant, contravariant. What are tensors? and how? Oh, then we get into Plücker coordinates. PLU umlaut CKR Plücker coordinates. And as with regards to, eventually it all works back to being Euclidean and Cartesian again. Differential quadratic forms, section 28, remarks on the case of an indefinite ds squared. We agreed to say that an n-dimensional V sub n space is metrically defined when there's associated with it a differential quadratic form with real coefficients out aik, that the phi or phi is the sum of the ik's over the ik's of the aik dxi dxk. And so these are these partials in terms of these not necessarily perfectly arranged or having the same angles together. So this is after the tensors are kind of set up, and over the course of the range of these things, these are not constants. And so taking the partial in two different dimensions that makes it usually the idea of vector addition in a linear space is that, well, those would add back up, but they don't in an arbitrary space. So we see what it says. We then introduce the hypothesis that phi is definite and positive, and this is the only case we have considered in the foregoing sections. We now propose to make some remarks on the case in which phi is still supposed irreducible, or such that its discriminant a is not 0, but is no longer definite, being capable of taking positive values for certain sets of differentials dxi and negative values for certain others. So this kind of reflects on the ideas like, well, when things are quadratic and not nil square, but that produces the analytical character of measurable regions of the quadratic, and then when they're nil square and when they're like anti-nil square, or in as with regards to they go the other way, coming together or going apart, say. In this case, fixing a generic point P of coordinates xi and an infinitely near point P prime of coordinates xi plus dxi. So, and that's established with their being connected and infinitely near, or otherwise not to like being a degenerate point or an extended body or anything like that, which we shall call ds squared, which can now be positive, negative, or 0. The square of the line element, the distance or Bethe interval between the two points P and P prime. Among the infinity to the n real systems of differentials dxi, or as we shall say, considering only ratios among the infinity to the n minus 1 directions drawn from P, there are infinity to n minus 2 which satisfy the quadratic equation when the ds squared equals 0. For a moment, we shall interpret the differentials dxi as referring to Cartesian coordinates with the origin P. Then the directions just defined, which are said to be of zero interval, constitute a quadratic cone of vertex P. This cone divides a sheaf of directions drawn from P into two regions, one of which d is squared greater than 0 and the other d is squared less than 0. All the directions which the first region are said to be of the first kind are time-like. And here he's immediately attached it to a totally different concept with regards to having independence of variables and some of the treatments of geometric interpretation in relativity theory for the time-like, the light-like, and the space-like. But to continue reading, all the directions in the first region are said to be of the first kind or time-like, the terms being suggested by the interpretation given these symbols in the theory of relativity. Those in the second region are said to be of the second kind or space-like. And so that's just for reading that in the Laplacian, there's three terms that are in time terms and one that's in space terms. And then there's the light-like as well. And so here it's just with regards, one of those is positive and the other one is negative. So it's just a name given to these, reflecting on that, if not necessarily so attached to that interpretation. Only that it's so attached in that particular attachment of the interpretation. The parameters of a direction of either kind are defined by the formulae lambda I is equals the dxi over the absolute value of the ds. There is no analogous result for the directions of zero interval corresponding to which ds squared equals 0. So it's basically given, it's like, okay, from now on we're only working in the half plane. We're only working in, these must be kind of like from a perspective only facing one way. That's its cone. That's its quadratic cone. It's its future and all that kind of stuff. Whereas it doesn't describe things. Well, what happens when it's an extended body? What happens when it's a degenerate body? What happens when matters of scale and proportion are like through and through, vis-a-vis just about and around? So, but that's his definition. So that helps establish these are some of the indefinite cases. Granted these results, the systematic extension of the preceding section to the indefinite case would certainly not seem likely to be difficult from one side. There might not be much in the way of being able to go back, say. As we are not aware that this has yet been done exhaustively, the reader's attention may be called to it. We propose merely to point out an extensible fact, almost evident a priori, and often used in theory of relativity, namely that definitions, geometrical representations, and formulae in the foregoing sections can certainly be carried over and applied to the indefinite case, provided A, that we take account of the exceptional behavior of the directions of zero interval, and B, that we make the obvious formal modifications necessitated by 59 when we have to deal with space-like directions. Where 59 was the quadratic identity is satisfied by the parameters lambda i's, that it's square is the idea. We leave the matter here with two examples to conclude the discussion. The condition that two directions, whether time-like or space-like, about the Laplacian here mostly, if we consider only lines, only composed of time-like elements, the discussion holds without modification. So that just helps to show that that's where then there's kind of like given that would be part of like the Zolfi metric and also about Bianchi-Beckland and Ricci Reggi is with regards to their placement and anywhere you see anything like negative time or anything that has no attachment but is just used as like a mathematical mechanism to get either like a foothold or some breathing space, that's just an example of one of those kinds of things. It's lost half the plane to gain kind of a perspective of things, or given it away rather say. Fundamental properties of Raymond's symbols. So this has more to relate to than the Azadides things. Then getting up into Lorentz transformations. And so he's getting into describing various kinds of solutions to the Lorentz transformations. In this case, in the hyperbolic trigonometric functions, as with regards to the hyperbola and the trigonometric functions. That a hyperbola is like A circle is isoparametric, and like given an angle bracket, it would if you consider the box that it would fill, if it was inscribed in a square, a circle, and then also as with regards when you flip that around, and then the hyperbola would be as if the whole quadrant, it would just be almost look like just the angle of that square. Yet the hyperbola is that angle, and then the circle is the isoparametric form between them. What those mean to scale back and forth between each other in the unit box and in the infinite quadrant. That was discussed quite a bit in the ideas of the identity dimension and the hat analysis. And it mentions Romer, R umlaut, MER, and Lawrence, the Romer unit of time, and these ideas. They contain the best known results, to some of which eminent students of relativity have assigned paradoxical consequences of the kinematics of relativity. So, this helps go to show that this is kind of part and parcel of the language of this field. All right, looking at another book here. Oh, this is a theory of matrices and numerical analysis. So this would be as with regards to numerical analysis, usually numerical methods, and forms as with regards to the names of and the forms of transformations and factorizations, and with quite an extensive bibliography of Householder's theory of matrices and numerical analysis. Let's see, what's this here? Distancing graphs. This is Harari and Buckley. This is not yet so relevant here, but when you think of something like the tensorial analysis, and the idea is like, well, we just have a continuous manifold, and we're just trying to figure out the length of the distance and the metric on the norm. And that in graphs, when you have like, well, how many hops does it take vis-a-vis how long are each of these vertices, edges? And so the continuous manifold is a smooth continuous. As a graph, it's got infinitely many points on the graph between any 2 points. Yet at the same time, it's modeled as by the modular in this lattice that the metric and norm are these modular increments, all of the same length everywhere. And in any given region that's bounded, there's finitely many of them. An Introduction to Ordinary Differential Equations, Coddington's Introduction to ODEs. That's a pretty good little book. Boundary value problems. This is a college textbook. This is Power's boundary value problems, and so this is a great little textbook, and this is what I studied. Harcourt Academic Press. This is about 1995 or something like that. 1999, originally 1972. This is the principal objective of this book is solving boundary value problems involving PDEs. And then it goes on to develop D'Alembert's solution of the wave equation. So here, there's much interest also in D'Alembert's integral equations, and with regards to Clairaut and D'Alembert and the linear fraction equation. This is Differential Equations, Introduction to Qualitative Theory by Jane Cronin. From Pure and Applied Mathematics, a series of monographs and textbooks. And this is from Pure and Applied Mathematics, and Dr. Cronin is from the Department of Mathematics at Rutgers, and this was printed 1980 by Marcel Decker. This book has two objectives. First, to introduce the reader some basic theory of ordinary differential equations, which is needed regardless of the direction pursued in later studies. And second, to give an account of some qualitative theory of ordinary differential equations, which has been developed in the last couple of decades, which may be useful in problems which have arisen in quantitative studies in chemical kinetics, biochemical systems, physiological problems, and other biological problems. The only prerequisites for reading the book are the first semester of a course in advanced calculus and a semester of linear algebra. So usually after a multivariate calculus or like Calc 3, then they'd have what they call advanced calculus. And so it just kind of gets up to solving like Green and Stokes and stuff like that is the usual idea. And then they get into ODEs and PDEs and these kinds of things. Talking about stability. Unaccounted for disturbances. See, the idea that every differential and integral system is an integro-different and different integro system are some of these unaccounted disturbances that are always is this sympathetic resonance or remnants and some of these other terms that really have meaning in also the measurable in terms of like electrical systems and this kind of stuff. That these are some of the kinds of things that help to describe what's going on with these things. Stability conditions, linear theory, the Jordan curve theorem, Poincare-Bendixson, basic results, LaSalle and Lefschetz. So that's our algebra, our famous algebraic geometry, which is a geometer's Sells theorem, classical branched, Coddington and Levinson, Hopf bifurcation theorem, and it was regards to singularity theory, multiplicity theories, branches, U.S. Army Research Office. Introduction, existence theorems, linear systems, autonomous systems, stability, the Lyapunov second method, periodic solutions, bifurcation and branching of periodic solutions, Scolio's theorem, principle of contraction, mappings, topological degree, Brouwer fixed point theorem, Jordan curve, and the Schauder fixed point theorem. So that'll be interesting to look at a little bit. Arnie Broman, Introduction to Partial Differential Equations, from Fourier series to boundary value problems. Talks about orthogonal systems, orthogonal polynomials, up to the Laplace transform, Bessel functions. PDE is the first order, PDE is the second order. So it's kind of nice that he introduces Bessel functions and kind of like the analytical tools that are going to be in the grab bag toolkit, and then gets into the solvers. So it's not like in the middle of like a thing, it's like, oh, by the way, the only thing that we might think that most people would know would be Bessel functions. It's like, first is like, these are Bessel functions, and they draw all kinds of nice curves, and especially when you learn the convolutive setting, they're just kind of back and forth. That would be great. What's this here? Differential Equations with Applications and Historical Notes by George F. Simmons. So this book is from George F. Simmons from Colorado College with a new chapter on numerical methods by John S. Robertson of the United States Military Academy from McGraw-Hill in 1972. And the table of contents tends to consider the nature of differential equations, separable equations. Talks about growth, decay, chemical reactions, and mixing, the brachistochrone, Fermat, and the Bernoullis. First order equations, second order equations, linear, qualitative properties of solutions, power series solutions, special functions, Fourier series and orthogonal functions, PDEs and BVPs, boundary value problems, some special functions of mathematical physics, Legendre polynomials, Bessel functions, gamma function, Bessel functions, Legendre polynomials, Bessel functions, Laplace transforms, systems of first order equations, nonlinear equations, calculus of variations, existence and uniqueness, and then numerical methods, Newton's method, Euler's method, advanced calculus. So this Witter's advanced calculus was a pretty usual text for advanced calculus. That's kind of what's called the course here. And it has stuff like differential geometry, vectors, PDE, partial differentiation, applications of partial differentiation, differential geometry. Here when reading differential geometry, and these days it's kind of like the submersions and immersions and this kind of stuff. And then it's kind of like it's kind of cornered itself a little subfield by painting itself into that corner. That's definitely, it makes some things sensible, fungible, and tractable, but it makes other things erased and lost. Limits and indeterminate forms, L'Hopital's rule and thereof, Rodriguez's formula and thereof. I imagine that's mentioned. It's consequent. Convergence test, and then there's talked after these laws of large numbers that there's various reasons to get into why and why not convergence tests work, and sometimes they don't. So, like with Stirling's formula, or for various means that have arrived at approximations for the factorial, which is the product of all the numbers, because there are different laws of large numbers, because there are different models of large numbers when, for example, there's a prime at infinity or a composite or infinity, or a quadruple prime at infinity, or these kinds of things. Whereas there's the only triple prime in all the finite numbers is 2, 3, and 5. So uniform convergence and these kinds of things. So it's getting into the analysis and how to establish the behavior and to prove the rates of convergence and these kinds of things with regards to integrals and derivatives. Well, we're coming up to time here, I suppose, for one of these usual episodes. Linear differential operators. Cornelius Lanczos. So here's Lanczos, L-E-N-C-Z-O-S. And so this gets into the operator theory. When it's discussed here that mathematics is kind of like geometry and number theory, and then arithmetic and algebra and analysis. Then there's function theory and topology, and then operator calculus. This gets into what's going on with linear differential operators. And so those don't necessarily require a complex space, or as with regards to a Hilbert space, these can happen in the Euclidean space, whereas equipped with a Cartesian origin and these kinds of things. Well, gentle readers, I hope you've enjoyed today's Logos 2000, since after a brief hiatus. Oh, I shall so hope to kind of pick up from after the colorless green and the theory of color. And then there's that's for the physics side of it, starting from the visible and the optical and this kind of thing. Then there's for the natural continuity and natural infinity, and then getting into the continuous manifolds and the continuous functions and the continuous topologies and otherwise these factors and features that go into what makes them monism, that's a mathematics as well. That'll be among these kinds of things. And then as also to get into the some of the original concepts to be able to employ as basically was set out in the beginning of this episode, that the integral and the differential are not merely inverses and complements, they're also inseparable in this sense. Well, have a great day.